All right, it is 4 o'clock. I'm Dr. Taylor, and this is the Exam 3 review. It is 4 p.m. on Sunday, October 17th, as it luckily says in the top right-hand corner of my computer monitor, so that I know what day it is. So we're going to start off where we often start off, which is what is on the exam. So this is Exam 3. We're covering Chapter 4, 4.6, and 4.7. So these were things that had to do with the electron configuration of ions, which I've got some examples we'll talk about of ions, and ionic radius. So that's what's in that last little bit of Chapter 4. Essentially, y'all may or may not have noticed it, but on Exam 2, everything was neutral, and now no longer the case. So now we will be adding electrons, taking away electrons, and figuring out what's going on when those things happen. Chapter 5, we're covering the whole thing. This is mostly nomenclature, and this is also where the math is for this exam. So this has things like molar mass, percent composition, and how to get empirical formulas from percent composition. And I've got an example of that as well. And then Chapter 7, it is the last thing we cover before the exam. It also probably has some of the most things you guys might want to study more of, because it has a lot of concepts and applications in it, and a lot of different pieces and parts to Chapter 7. Also, Chapter 7 relies heavily back on Chapter 6. We've talked in the past about what things wind up coming back, what things may or may not come back. This exam is really strange for this, because we have things like in Chapter 5 also has lattice energy. And lattice energy has a little bit of things where you might need some periodic trends, perhaps. Chapter 7 winds up still needing most of Chapter 6. So we still need to be able to draw Lewis structures. We still need those. We still need polarity of those bonds. We still need all of that stuff. And there's one other thing that happens towards the very, very end of Chapter 7, where we actually need stuff we haven't talked about in a long time, which is this notion that if I have orbitals, that if I have both of them, and we're going to say that these are centered on the y-axis, we're going to go with that being y and this being x, that these are both py orbitals. And if I had some of them that were coming out and were focused on the x-axis, we would call these px orbitals. So a little bit of this actually comes back towards the very, very end of Chapter 7. So this is a unit where there's a variety of different things that do come back into play. Chapter 5, you'll also see bits of that atomic mass and calculations coming back. So there's a lot of different pieces that we've learned about previously that actually do come back into this unit. So some of the questions that you all sent in ahead of time, I wanted to make a general statement, and I'll try to give you guys some examples as we go along. So someone was basically asking for things like, how will questions be phrased? What will questions sound like? Can we do some specific examples? I will do my best on that. The hardest part is that I only sound like one person. So I can do my best to point out when some words might be interchangeable, to point out what some different things might sound like. But at the end of the day, I only sound like me. I only sound like one person. One of the things I would really recommend you do is spend some time, two things. One, with the end of chapter questions, because those do have things worded differently from Alex. So it's another way to get different kinds of questions. The other thing is when you guys go to lab, you're usually around folks from other sections, which means you suddenly have access to students who hear a different professor and they hear how a different professor talks. So I would recommend that you make some acquaintances with people from other sections and spend some time chatting with them about chemistry, and listen to how they talk about chemistry, and listen how you talk about chemistry, because there's a lot of different language pieces that you guys pick up when you're in class and when you're listening to videos and when you're getting some of that information. So trying to put all these pieces together is really useful. I have that note on there that why ALEX isn't enough. ALEX is a tool that we really enjoy because it does a lot of good things. It does things like instantaneous feedback, and it also has that thing where if you have forgotten how to do something that we think you remember, it will remind you. We love this about ALEX, but it does have that configuration where it's going to ask you very similar questions over and over and over again. So it doesn't do nearly as good of a job of preparing you for problem solving. The questions are not in a random order. They're all fairly nicely labeled. Hey, this is what we're doing. And so you're missing some of those things, which is, oh my gosh, what is this question? What do I need to do? And what's going on? The other thing I've been recommending people do about that is to go ahead and get together with one or two other people and try to challenge each other to write true false questions. I know no one wants to do this, by the way. When I recommend this, I understand that nobody wants to, but understand that your textbook is going to tell you things that are true. ALEX is going to tell you things that are true. Even doing the end of chapter questions, they're aiming for things that are true. We don't have a set of practice true false questions. So the way to find false questions is to sit down and see if you can change a definition to make it false. Take a look at the definition for lattice energy. How many words does it take for you to change that definition to make it something that's now false? So we'll try to take a look at some of that as we progress. So one of the questions I got from the beginning, from the things folks submitted early on, is they asked a bunch of different things that I recognize as all being out of chapter 9. So a quick reminder for those of you that have either older siblings or have gotten a hold of previous exams from previous semesters. Those exams, we used to do 4 exams in a semester, and now we are doing 5 exams in a semester. That is different, and the material is therefore not all grouped together in the same way. So if you have an older sibling that took this class in 2018, their exam 3 looks a lot different from your exam 3. So depending on what year it was, depends on where the material is, and will depend on where you can actually find the questions that you're looking for. This, by the way, is the main reason that we do not supply you with old exams, because all of the material is in a different place, and it's frustrating at best. So instead of giving y'all tools that are outdated, we've just had you guys prepare for the material from the ground up. So the people that were asking about things like stoichiometry, that involves chemical reactions. Chemical reactions is chapter 8, by the way. So this is chapter 8. The types of chemical reactions, that's chapter 9. Solution concentration is also chapter 9, which is not on this exam. So this is all going to be exam 4 for us. So I will not be answering questions about this. Some of this stuff, empirical and molecular formula and some calculations, that actually does go back to chapter 5, that we'll talk about. But a lot of this stuff is actually chapter 8 and 9, which is exam 4 material. Were there any questions so far on kind of intro stuff, what's on the exam? It's Saturday, October 23rd. It's at 10 o'clock in the morning, and y'all need to log in no later than, I'm going to say 10:15. Technically no later than 10:30, but honestly, sometimes your clock says 10:28 and e-learning's clock says 10:31, and you don't want to play that game. Also, if I say 10:15, that way when you sit down and realize that your laptop charger is in your car, you have time to go and run and go grab it before sitting back down again. So that's why I'm going to say between 10 a.m. and 10:15, because that way you'll be in on time. Any questions so far? I'm not hearing any. So either I've lost connection with everybody, or everybody's muted, or there aren't any. So I'm going to cross my fingers that the answer is that there aren't any. And at 4:30, I'll take a longer pause and make sure that everything's connecting like it should. I know they used to have my cell phone number in case things went horribly, terribly wrong.
So far, there are no questions, Dr. Taylor.
Okay, fantastic. Thank you.
Yeah, no worries.
I was nervous. All right. So something else that people were asking about was configurations of ions. So this is out of chapter 4. So when we take a look at configuration of ions, zoom out, give myself a little bit of room. One of the most important things to remember, let me grab my periodic table, is that whenever we are removing electrons, we are going to remove those from the highest value of n. And this is one of those things where we talked about this as the definition of valence electrons. And in the beginning, it didn't particularly matter because we could talk about electron configuration of ions, and we could talk about things like oxygen. So for oxygen, we know that has that helium noble gas core, and then it's going to have that 2s2 and 2p1234 for my neutral set. And then if I want to talk about oxygen with a -2, this then is going to be what we call isoelectronic to a noble gas. Isoelectronic really does mean to a noble gas. This means it's going to have the same electron configuration. So iso means same. So we're talking about the same electron configuration. In this case, oxygen is going to be trying to look like neon. It's going to be gaining electrons. So while we could just say, ta-da, it looks like neon, we'll go ahead and write the whole thing out just so we can see where those electrons are going. So here's my beautiful noble gas core, 2s2, 2p6. So there's now my electron configuration for oxygen. So all we're really doing is filling out that 2p subshell, putting in electrons, and completing that 2p subshell. A lot of times where the more interesting ones come in are somewhere in our transition metals. So for example, let's go ahead and do vanadium. So if we were looking at vanadium as a neutral metal, this is going to have a noble gas core of argon and then 4s2, 3d3. The next thing we usually do for ions is with metals, these should be cations. So if I had something like vanadium 2+, now I have to decide where my electrons are going to come from. I should be removing valence electrons. So I should be removing valence electrons, and these should be the highest value of n. When I look at the electron configuration I have so far, 4 is greater than 3. So when I say that highest value of n, they should be coming out of that 4s subshell, at least to start. So, and I'm looking for a +2 charge. So I should just be left with that argon noble gas core and then 3d3. And that's then my electron configuration of vanadium 2+. If I needed to remove more electrons, I would then go ahead and go to my 3d3. So if I was looking for vanadium 3+, I'm taking away either 3 electrons total from the neutral, or I'm taking away 1 more than what we did before. I would still have that argon core, and then I would head into those d electrons, but only after I've removed the s electrons. So there's a lot of different ways we can ask questions with this, because we can do things as simple as just what is the electron configuration for vanadium 2+. We can certainly do that, but there's one of the end of chapter questions in chapter 4 actually asked something like, which of the following, so I think it had you rank them, but I don't have that exact question ready to go. Which of the following has, let's say, 2 unpaired electrons? And then we're going to use the examples that we've done so far. So I'm just going to use my vanadium 2+, and my vanadium 3+ as examples. So unpaired electrons, this is going back to thinking about orbital notation for this. So when we were looking at these 3 different options, here's my neutral. I would have had that 4s2 and that 3d and 1, 2, 3. So there's my neutral set. I have 3 unpaired electrons here. In 2+, my 4s is empty, so there aren't any unpaired electrons there either. And then my 3d3 again, I have 3 unpaired electrons. Coming down to vanadium 3+, my 4s is again empty. I have a 3d subshell now with 2 electrons in it. So my 2 unpaired electrons winds up being my vanadium 3+. So trying to take a look at how could we word things in a strange way for electron configuration. We could actually go back to orbital diagrams, even in electron configuration of ions, because that orbital notation is just another way of looking at electron configuration. And there's an end of chapter question that has, I think, 4 different metal ions to rank. So in a nutshell, that is electron configuration of ions. Main thing is in transition metals to make sure that you're taking things out of the highest value of N. So making sure you're grabbing those s electrons first. And then these are also where that isoelectronic to a noble gas phrase could potentially come in, because all we're doing is we're looking for the same electron configuration of a noble gas with that isoelectronic wording. Now I'm going to scroll back up to my outline. So that was electron configuration and the retouch on isoelectronic to a noble gas. Okay. My next topic that I've gotten written out is lattice energy. So I went ahead and wrote out some things to rank. And then someone asked about Coulomb's law, and I had some other people ask about the lattice energy formula. So put that down here. So what we are going to do is we are going to rank from least to greatest lattice energy. And we're going to make these bigger. So I was trying to find ways, that's actually not what I wanted. I was going to make the font bigger. So what I was trying to look for is ways to kind of throw in nomenclature, because no one really asked about nomenclature, which is fine. I'm going to assume then that y'all are doing amazingly and awesome on nomenclature. So all I'm really going to do is throw some nomenclature into some of my examples to show you some places where it can show up. So the first thing I'm going to need to do is figure out what all of these actually are. So you'll notice that all of these have iron. So all of these have iron. So I'm going to go ahead and grab my chemical symbol for iron, which is Fe. And that is one of my transition metals. So luckily, in all of my words, in parentheses, in Roman numerals, it's telling me what that charge is. So this is Fe2+, this is Fe3+, Fe3+, Fe3+. And then I need chloride. So I'm going to scroll back up to my periodic table. So here's my chloride. It's in group 7A. It therefore should have a -1 charge. So chloride, and chloride, and then I've got oxide and sulfide to worry about. So I'm going to go find my oxygen and my sulfur. Here's oxygen, here's sulfur. They're both in 6A. They're both going to have -2 charges. I'm going to go ahead and form my compounds just for practice. So this should be FeCl2, this should be FeCl3, Fe2O3, and Fe2S3. If I'm trying to talk about lattice energy, what I should be thinking about is that there is a formula for this. The thing that's really nice about the formula is the formula lets me remember all the pieces and parts that I need. So I have charge and I have distance. This is technically the distance between the nuclei. The other thing I actually like about this formula is because the charges are on top, and technically there's a constant here, because that way we can make things actually equal. So this is also essentially Coulomb's law. So lattice energy and Coulomb's law have the same formula. Charges divided by something to do with distance. So my charges are on the top. My charges are actually the most important part of lattice energy. So the distance matters, don't get me wrong, but the charges are more important. In chemistry, my charges change by whole numbers, and my distance changes by little bits. My distance changes usually by decimal amounts. So I'm just not going to pay attention to distance because for right now, because what I've already seen is I've already seen my charges changing. So I'm going to focus on those first. Now you can go ahead and think about these as something that's being multiplied. This is the other reason why I do like the formula, is what you should notice is that this formula does not care that I have 2 chlorines. Doesn't care. The only thing that the formula cares about is that I have a +2 and a -1. I have a +3 and a -1. I have a +3 and a -2. I have a +3 and a -2. And that's all the formula really cares about. So therefore, I do not care how many of each one I have, because technically with lattice energy, we are taking 1 mole of ions and separating them. So I don't care what kind of ratios they're in, aside from if it helps me figure out what their charges are. Charge is all I care about right now. The other thing with this is that the greater the charges, the greater the attraction between them. So if I'm looking for least to greatest, what I'm going to start off with is I'm going to put the lowest charges are going to have the lowest lattice energy. So I can go ahead and put my iron 2 chloride down here, and then my iron 3 chloride here. And then I do know right now that my iron 3 oxide and my iron 3 sulfide are somewhere in the greater set, but I don't know which one's which. So I can rank my +2 and my +3 with their -1s. Those are going to be lower lattice energy because their charges are smaller. Oh, but then I've run out of the same charge, and all I have is 2 things that are exactly the same. Darn. So now that I actually have 2 that are identical charges, now I have to go and figure out the distance. So now I will worry about distance. What you should notice is that both of them have iron in them, so all I have to worry about is my oxygen versus my sulfur. This is where what you should realize is we're often going to do this kind of a game where what we have, erasing some stuff so I can see, is I have 2 elements that are one right on top of the other. So yes, they are ions. So we could talk about ionic radius, but they have the exact same charge. So the only thing I really care about at this point is the fact that one of them is a higher value of N than the other. One of them is higher on the periodic table. So these are going to have different sizes, but I can actually do that based on that old Bohr model of the atom, based on how many values of N do I expect to see, and therefore which one is going to be larger. So all I really have to think through with oxygen is that oxygen is in that N equals 2, so I expect it to look something like that. And sulfur is in N equals 3, 1, 2, 3. So I expect sulfur to be larger. Since it's larger, this means that its nucleus is going to be farther away from the iron. So this is farther apart. Farther apart is going to mean a weaker lattice energy. This is because if you've ever played with magnets before, the farther away they are from each other, the less they can feel each other, the less that attraction has power over each other. So the farther away they are, the weaker the lattice energy. And it is. If you've ever played with magnets, you know that basically the closer they get together, the easier they can just snap together. So closer they are, easier they snap. Farther away they are, the weaker that attraction actually is. So I can then go ahead and put next up my Fe2S3, my iron 3 sulfide, and finally the one that's closer together is going to be the stronger lattice energy Fe2O3, iron 3 oxide. So that goes ahead and lets us rank our lattice energies, charge first, then if you have to break a tie, size next. Questions so far? It's almost 4:30.
There was a question when you were talking about electron configuration.
Mm-hmm.
What about elements with the p block in the shortened electron configuration? Would the p subshell have a higher N value?
Oh. So let's do one of those. Let's go ahead and do 10. It's hanging right there. So for 10, again, I'm going to go ahead and draw the neutral form first. So that is krypton, and then 5s2, 4d10, and then 5p2. If I want 10 with a positive 2 charge, I'm still looking for highest values of N, but now I actually have 2 of them. So if I do have 2 different values where I have the highest value of N, now I can go ahead and choose the higher subshell, the higher energy subshell. So I am going to go ahead and remove first from that 5p2. So I'm going to leave my 5s2 and my 4d10, and the first place I'm going to remove from is that 5p2. Oops, I should not have forgotten my krypton noble gas core. It's in there. So right, so if you do have ones where you have that p block and you're removing electrons, you are going to remove out of the p subshell first because you've got the exact same value of N. You've got 5s2 and 5p2. So when you're looking at those and they have that same value of N, you'll go ahead and select the higher subshell. And just to, again, remind that then if you go to look at it with a 4+ charge, now we'll go ahead and still maintain that highest value of N. And now we're down to 5s2, and it looks like this. I don't know if y'all have gotten to do some practice, but 10 usually does have 2 most popular charge states, and those are a +2 and a +4, and this is why. So those electrons do actually come first out of that 5p2 and then out of the 5s2. And y'all might have actually noticed that out of that transition metal, that D block, a +2 charge state is really common. So you see that a lot in those metal ions. But no, it's an excellent question. So trying to debate between subshells, pick the higher subshell. Excellent question. other things so far?
Nope, so that was the only question so far.
Okay, sounds good. So we did lattice energy, and essentially we went ahead and looked at that formula with lattice energy, which was that bit of Coulomb's law. So the next thing I have on here is nomenclature, and specifically the question was when to use prefixes. So some little bits of nomenclature can get a little bit tricky. So now into a nomenclature block. Super exciting. I've gotten better with nomenclature. It's just not my favorite topic because I feel like examples are really nice though. So when do we use prefixes? So typically, you're going to use prefixes when you have a molecule that is covalent. Now, along with that, that is typically all nonmetals. So we would use prefixes to talk about something like NO2. So this one becomes nitrogen dioxide. We would use prefixes if we were trying to talk about something like P2O5. So that one is diphosphorus pentoxide. So anytime you see a whole bunch of nonmetals, you're looking at something that needs prefixes. Now, there is somewhat of an exception to that because I have on here, but not this one, because while it is all nonmetals, nitrogen, hydrogen, and chlorine, you are actually supposed to recognize that this thing is a polyatomic ion. So this actually is ammonium chloride, because that is the ammonium ion. And yes, you may hear me enunciate that M on ammonium a little bit extra, and that's because NH3 is ammonia with just that IA on the end. So the two spellings are very, very similar, but one of them is a neutral compound with 3 hydrogens, and one of them is a charged compound with 4 hydrogens. So these two things are similar, which is why they have fairly similar names, fairly similar spellings, but they are different, and we need to differentiate between them. So do be aware that on your polyatomic ions list, there's, I think, only 2 things that have all nonmetals but are positive. One of them's the ammonium ion. I believe the other one is the hydronium ion. So any compounds that have either ammonium or hydronium in them, you need to be careful because these are actually ionic compounds. So anytime we're dealing with polyatomic ions, this then is held together with ionic interactions, because this is, going back to my ammonium chloride, that is then an NH4 plus with a Cl minus. So those two components are held together with ions. So this is actually an ionic compound. That being said, do realize that my ammonium is held together with covalent bonds. So ammonium, you could absolutely draw a Lewis structure for. It's held together with covalent bonds, but when it's in a compound with something else, the charge on the ammonium ion is what holds it together in a compound with other things. So this concept, by the way, where you have an ionic compound because that's what's holding the polyatomic ion to the chloride ion between my polyatomic and my chloride ion. But inside NH4 plus are covalent bonds. This idea can be a really nice time for us to ask you a true-false question. So we could very well have something where there is one that's talking about, and we would be specific. So I'm gonna have to write this out. I would also like this to be in a font size that y'all can actually read. So it might say something like this: the ammonium chloride compound is held together with, and then we would have more statements than this, but it might say something like the electrostatic interactions between ions. So there's A, and then B might be sharing electrons between the nitrogen atom of ammonium and the chloride nucleus. This is not the best language ever, but hopefully you get the idea that we are asking you about the entire compound. So we're asking about the ammonium chloride compound itself, and then asking you essentially, does that count as something that's ionic, or does that count as something covalent? And again, we would actually count that as being something ionic, because we don't actually have electrons being shared between nitrogen and chloride. So this part where there's electrons shared between the nitrogen and the chloride, this does not happen. This does not happen. So that's one way that we could potentially ask you about that. That being said, again, I gave you that other example talking about the ammonium ion. So we could ask you about the ammonium ion itself is held together with, and then we could say something like electrostatic interactions between ions. And we might add something like hydrogen ions and nitrogen ions versus, and I know I'm only giving you guys 2 options, which is not as many as we have on the exams, but with sharing electrons between the nitrogen atom and each hydrogen atom. So now that we're talking about one particular ion, now we are actually talking about what keeps polyatomic ions together, essentially. And when we're talking about polyatomic ions, these are held together with covalent bonds. So you would actually expect the polyatomic ion to be held together by that sharing of electrons. So again, those two look really similar. So it's going to be you reading the wording carefully, that one of them is just talking about the ammonium ion, just a polyatomic ion all by itself. And the other one is talking about an ionic compound. It's talking about the ammonium ion and a chloride ion that have come together to form one ionic compound. So both reading the question carefully to make sure that you know what we're talking about, to make sure that you're not thrown off and be like, wait, which one? Is it the polyatomic ion or is it hanging out in a compound? And then watching carefully to make sure that you're conceptually aware of what's holding everything together. Because this is the time where now we've got ionic compounds, we've got covalent compounds. So it's a nice time for us to ask you, how is this one held together? How is that one held together? And what's really going on? That was, oh, and to talk about prefixes. I was like, why did I go off on this rant? Because of prefixes. The last time where you need prefixes are for hydrates. So hydrates are another time where they're a little bit funny. So here's a hydrate. I'm going to use a lot of chloride, by the way. It makes my life easier. Because if I basically use the same halogen over and over again, you guys get a little bit used to the fact that that should be -1. I guess we'll use something different just for kicks and giggles. I'm still going to use a halogen, by the way. We're going to use bromide instead. So I would go ahead and scroll back to my periodic table because I don't think I can just copy and paste. Oh, it's getting way up there. I'm going to need this again. So what I'm looking for is I'm looking for that CO, which is hanging out over here, and my Br hanging out over here. So my Br is also in 7A, so it should have a -1 charge. My cobalt, I don't know what it is, but I know that bromine, my bromide ion now has a 2 by it. So since my bromide ion only has a -1, and there's 2 of them, this should be a +2. So when I go to write this out, this is going to be cobalt 2, putting that Roman numeral in parentheses, and hopefully I'll notice that there's no space here. Bromide, I don't need a prefix for the bromide because I basically looked up its charge on the periodic table. And then 7 is going to be heptahydrate. What? No. Oh, you are kidding me. Hold on, I must run around my house so that my laptop doesn't die. Where was my laptop charger last time? I know I warned you guys about this. Nothing like the thrill of will my laptop die. I don't usually carry my laptop around the house, but I was trying to be supportive of my partner who is working on his 2nd novel. And so in doing so, we were having my doorstop. We were having work time on the dining room table, which I forgot about. Okay, crisis averted. Phew. So now that my laptop's plugged in, all good, all good. I did not carry my pen around with me. I left it here, all good. So there should be no space in between the cobalt and the Roman numeral. And then we do need to talk about this thing on the end, which is a hydrate. So we are using a Greek prefix to describe how many waters are there. So hepta is a Greek prefix. And then the other thing we have here is the word hydrate. Likely y'all have heard the word hydrate before, even if y'all have not been in Texas for that long. Y'all got here in August and you probably heard people tell you to carry water around with you and to stay hydrated. So hydrated for the word water. And so that heptahydrate is just describing that there are 7 waters. So those are the 2 main times you need prefixes. That was the whole point of all of this, is you need prefixes when you are dealing with covalent compounds. You'll usually know that they're covalent compounds because they're all nonmetals. Watch out for the trap, which is ammonium, the ammonium ion, and occasionally the hydronium ion as well, because so those are ones that are positive but are not metals. And then the only other time that you're going to need a Greek prefix is to deal with hydrates. And then there's a couple questions about acids. So before I go to acids, I'll go ahead and address this question. Do we know the name of simple alkanes and functional groups? No, you don't. This is always a good question. I usually chat about them in my class and tell them that I just like them to know that there is more nomenclature out in the world. So if you go to the grocery store or you go to Walmart and you buy isopropyl alcohol or isopropanol, you guys realize that that actually is the right name for that particular compound, but that's something that's covered in organic chemistry. So if you guys do come across different kinds of nomenclature, don't think that they just made it up and gave it a really cool nickname to make more money. That's actually what it's called. But we will not test you on those. We just like to make sure that y'all know that there is actually more nomenclature than what we've covered in this course. But we save those for other classes. So the other one is about acids. So here's the thing with acids. So I've got some examples, and then are they going to tell us to write out as an acid, or do we figure out if the molecule is an acid or not? So that is one of those questions where it depends on the person who wrote the question. So these can look a couple different ways. So sometimes it just says something like, name the compound, and that's all you have. Maybe it's very straightforward and that's all it says. If this is all you've got, the fact that you have a hydrogen in front, and it's neutral. That's not how we spell neutral. And the fact that it's neutral, this is going to be enough information to go ahead and assume that it's an acid. So you could also see something like H2SO3, no other information, and you are also going to say, all right, I've got hydrogens in front. The whole thing is neutral. I'm going to assume it's an acid. But we could give you more information. So hydrogen in front, the whole thing's neutral. Without any other information, assume it's an acid. But wait, there's more. We could do something that's a little bit strange, but is allowed. These are the same, except for the state of matter. This is a gas. This means aqueous, which means in water. This is an acid. It has a hydrogen in front, the whole thing's neutral, and it's in water. This, not an acid. It's got a hydrogen in front, the whole thing's neutral, but it's a gas. Gases are not acids. Acids have to be in water. It's part of their definition. So this is one of those times where it's a really excellent question. And I have not looked at the exam questions yet. So I don't know if they're going to do the game of all you have is HCl with no additional information. If we don't specify the state, you can assume that it's an acid. But if we specify the state, or if we're asking you to find the acid, then you need to be careful and you need to watch out and make certain that you found something that has that AQ symbol after it. Because the AQ symbol means in water, and that does then mean that it's an acid. So we do name these two different ways. Since we've talked about the acid a lot, we're going to name the acid first. So this is what we term a binary acid because it's hydrogen and one other element. This is just hydrochloric acid. So really the only thing for all of your binary acids you're going to wind up doing is swapping out this middle part for the element that is listed. Otherwise, the hydro is for the hydrogen and the ic acid is for the acid component. So usually I just start off with hydrochloric acid because that's usually something that most people have heard of between like true crime podcasts and the news and other things. So Hydrochloric acid is usually a nice place to start. And then you can just basically find the place where there's your chlorine atom. I'm just going to switch out the chlorine for something different. The gas is a little bit strange because we often name things with hydrogen in them as if they were ionic. So this is actually hydrogen chloride. So we actually often treat this as if hydrogen was a metal. That is one of those that really almost falls into the old nomenclature rules, but there are some good reasons for this. But in general, when you have that hydrogen in one other element and it's a gas, you actually do name it as if it was an ionic compound, even though it's not. So someone had also asked about the differences between binary acids and oxoacids. So this hydrochloric acid is an example of a binary acid. I wanted to give you one more example of a binary acid because some people do latch on to this idea that binary means two, which is correct. But the binary part is binary because it's two elements, not because it's two atoms. So every once in a while, y'all forget that you can actually make binary acids out of chalcogens. You can actually also make them, which is group 6A. You can actually also make them out of group 5A. Those also work. But usually the most common ones are out of halogens or chalcogens, because after that, their acidic properties usually aren't so great. So all I'm going to do is I still need the hydro part. I need a part that sounds like the element, and I need ic acid. So I'm going to look up what Se actually is. It's selenium. So all I'm really going to do is grab this part and put it down there in the little blank spot. And you have hydroselenic acid. So binary acids, two elements. Oxoacids, which yes, does mean with oxygen. These are going to come from your polyatomic ions. From polyatomic ions. So you can essentially go down your list of polyatomic ions and make acids out of them. So for example, here is sulfite. It has a -2 charge. I'm going to add 2 hydrogens to it to cancel out the charge, because we are essentially adding H+ to cancel out the charges. Then when I name this, I'm going to keep that beginning part of my polyatomic ion that I had, but then I need to change the ending. When it's ITE, I'm going to change this to OUS. That's not an S, that's an R. Except I need a couple more letters because that's how this one goes. Sulfurous acid. And then this one, which is based on sulfate, is sulfuric acid. We could get fancy. And this is oxalate, H2C2O4. And this actually does become oxalic acid. So whether you have one where it's the ite and ate, and you've seen those pairs before, or even if it's one that I'm not actually certain that there is an oxalite as a compound, but we still use the same general rule which is to remove the ATE and add IC and acid to it. So oftentimes you either see these with the OUS, if it's adding an ITE, or if it ends in ATE, adding the IC. The only other ones that are a little bit funky is if we had something like this, HBRO. So this is the hypobromite ion. And so this one is actually hypobromous acid. Shouldn't actually be as a surprise. We have that ITE ending, we have the OUS ending. So that part is all the same. So just realize if there are any prefixes, then you're still going to hold on to those. So that hypo is another prefix, but it goes along with the polyatomic ion. So when we go to write the acid name, it comes along for the ride. I'll go ahead and give y'all the same general spiel I did with polyatomic ions I gave my class. When y'all are looking at your polyatomic ions list from the textbook, the textbook, for some bizarre reason, lists everything in alphabetical order. I really wish they had not done that, because alphabetical order is really not helpful, because they separate out things that naturally go together. So there are 4 different polyatomic ions that all have chlorine in them, and you have to kind of run around that chart to actually find all 4 of them, because they're not all in one place, because 2 of them have prefixes and 2 of them don't. So just be aware when y'all are looking for your polyatomic ions that good news, bad news, the chart in your textbook is in alphabetical order. So the good news is now you know it's in alphabetical order. They had to pick something, that's what they chose. But bad news is that they're not organized by charge, they're not organized by element, they're not organized by any chemistry property at all. They're not organized by a chemical property, they're organized by a literary one. So now you know. Now you know that's how your book organizes the polyatomic ions. Which I guess is good, because it hopefully encourages you to reorganize them, because alphabetical order is not super useful. Okay, things we've talked about. Nomenclature, when to use prefixes. We talked about how to figure out if it's an acid or not. Do we know the alkane functional groups? Nope, but we did talk about that. And the difference between oxoacids and binary acids. We did all of those. And we are about to 5 o'clock. So any questions so far?
Yes, we have a few questions about nomenclature. Someone asked, when you were going over the ammonium chloride example, could they also say ammonium monochloride? Would that be a correct name?
So it would. So the question is, let me bring it back, about how to name this. So because ammonium chloride is an ionic compound, it is held together with electrostatic attractions. It is held together by having a positive ammonium ion and a negative chloride ion. The only correct name for it is ammonium chloride. So if you were to put in a Greek prefix in there, it would be wrong. So because it's held together with electrostatic forces, there's only one way to name it, and you do name it as an ionic compound. So excellent question for clarification, and there's only one name for that, which is ammonium chloride.
Okay, and someone asked if there are any ions they should remember, or what ions should we remember?
So from your book, sorry, I'm thinking about where the fastest place I would have this information is. So in your textbook, there is a flow chart for nomenclature. So as far as ions you should know, there's a couple things to do. There's polyatomics, and it's the chart out of your book, chart from book, plus And honestly, it depends on the year, but I'm going to go ahead and add these in. If Dr. Diekman on Wednesday then says you don't need them, that's totally fine. But I'm just going to cover my bases. What I'm drawing out, I'm going to draw them first and then explain so that I don't forget. So from the book, are these. And essentially, what you should notice is these all look like they have something in common. So what happens is there's a set of polyatomic ions that all have chlorine in them. And if you swap out the chlorine for the halogen, for a halogen below it, for either for bromine or for iodine, you actually maintain the same name except for the element portion that's in there. So taking one of the shorter ones, this one is chlorite, this one is bromite, this one is iodite. So this idea that chlorine, bromine, and iodine are actually essentially interchangeable, and for where there were 4 polyatomic ions, there's actually 12. And all you have to do is name the element that it's part of. These are some that often show up in some of our questions because they are, because the set with the chlorines, hypochlorite, chlorite, chlorate, and perchlorate, we typically use these a lot. And these are so very similar to them, we often use these as well. So there's your polyatomic ions. The question was about ions. So the other set that I assume everybody knows is that there's your group 1A, which are plus ones, your group 2A, which are plus twos. There's your halogens, group 7A, which are negative ones, your group 6A, which are negative twos, your group 5As, which are negative threes. And then there's a couple that are just extra. Aluminum, silver, cadmium, and zinc. So there are a set of metals that always have the same charge. So if I were to use any of these, I do not need Roman numerals. So I would just say aluminum chloride. And I'm done. I do not need to say what the charge is on the aluminum because aluminum only has one option. I could say cadmium phosphate because cadmium only has one charge. Not that I can spell that. Cadmium, there we go, phosphate. Cadmium only has one charge. I do not have to specify what it is. As opposed to some of the other metals where I do need to specify the charge. So if I was doing something like copper, I need to tell you what the charge is on copper, and that's where those Roman numerals come in. So if I had something like copper 1 oxide, I need to specify what the charge is on the copper, because if everything's just all in words, there's a couple of options for copper. I need to tell you what that is. So group 1A, group 2A, aluminum, silver, cadmium, and zinc. I don't have to tell you what they are. They only have one option. You should know what that is. Your nonmetals only have one option. You should know what that is. Your D block elements, they can be all over the place. So your D block, your F block metals, all bets are off. But your nonmetals, I should specify that these over here are my nonmetals. Nonmetals in these groups. Some of those also have metals in them. Some of them have metalloids in them, but the nonmetals have those set charges. Okay. So I'm hoping that that answers the ion question. It's a good question. Which does not have a short answer, but hopefully that answers the ion question. Other questions?
Yes. Someone asked, ionic means a metal plus a nonmetal, right?
So ionic means a metal plus a nonmetal most of the time, but that's why we covered the ammonium chloride example. It's one of the exceptions. So as usual in chemistry, we have a set of normally, and then we have this idea that it's like, well, that's not entirely true, because the real definition of ionic has to do with how it's held together. And an ionic compound is held together by electrostatic interactions. That is charges. So you most commonly see this with a metal and a nonmetal. So you most commonly see there's a magnesium, there's a fluoride, and these are held together because the positive magnesium ion, which is a metal, is attracted to the negative fluoride ion, which is a nonmetal. So that is the most common way you see that, but that's why we were using the ammonium chloride example, because I still have a positive and a negative, but now my positive is a polyatomic ion. So my positively charged thing is still a positively charged thing. And that's all the definition of ionic cares about. Ionic compounds just care about what's holding it all together. If I've got a positively charged ion and a negatively charged ion, that's an ionic compound. It just so happens that you have a few positively charged polyatomic ions that are all made up of nonmetals. So ammonium chloride is an ionic compound. It is. It's got an ammonium ion that's positive. It's got a chloride ion that's negative. And I could even go ahead and put together ammonium oxide instead, just to give us some different. Ammonium oxide, also all nonmetals, but held together with electrostatic charges, held together because I've got a positively charged thing and a negatively charged thing. We could even do multiple polyatomic ions. Oh, you are not excited about this, I know. Ammonium phosphate. Even more nonmetals. Two sets of polyatomic ions coming together, making an ionic compound, even though they're all nonmetals. So again, this is that part where we expect y'all to know your polyatomic ions so you can recognize them. And I thought there was only two, but check. I think your table in your textbook actually has them delineated out, where I thought the cations were at the very, very top of the table to make sure you could see them really easily. Or maybe it's the fact that ammonium starts with the letter A and the textbook table is in alphabetical order. But there's not very many positively charged polyatomic ions. So therefore, you should be able to identify them. There are not that many. You should be able to know what they are and find them. Other questions or clarifications?
Okay. Someone also asked why ammonium chloride is ionic earlier, but I think you just sufficiently answered that.
Yeah.
Someone
that's
asked,
why I included it, because I knew it was gonna. I knew they wouldn't like it, and that's why I included it. Yes.
Someone asked, can you do acids for non-neutral compounds with a polyatomic ion?
So right now, so let me show you an example of what they're talking about, or at least what I think they're talking about. One of my favorite games. So there's another acid, which we would also name. So there's carbonate. I'm going to name this the same way we've done before. So if I add both of my hydrogens, this then becomes, I'm going to replace that ATE with ic acid. We'll go ahead and make this aqueous. This then becomes carbonic acid. Now, if we are talking about the ocean and ocean acidification, this is the acid in ocean acidification. Carbon dioxide combines with water to form carbonic acid. That's how that works. Right now, on your polyatomic ions list, you should be able to find this. I believe on your polyatomic ions list, they just go ahead and call this thing hydrogen carbonate. For now, we're going to roll with that. For right now, we're just going to say there is this other species that you might notice is kind of in between the carbonate ion and carbonic acid. But if you look, it actually, I believe, is on your polyatomic ions list as hydrogen carbonate. The same way that we could have named phosphate, and then we could have named phosphoric acid. And I believe they list both this guy and this guy on your polyatomic ions list. For right now, we are going to go ahead and just have acids be neutral compounds and the other ones be polyatomic ions. These actually are also acids, but we'll have time to talk about that in chapter 9, because we're in, this exam is the end of chapter 4, chapter 5, and chapter 7. Then chapter 8 is chemical reactions. Chapter 9 is aqueous chemical reactions, and we will do acids in chapter 9. So the person who's asking that, that is an excellent and a beautiful question and a really good connection between things, but we need a more robust definition of what acids are. And right now we're just naming them. So that's really, really excellent to be thinking about that. But for where we are right now, we're just naming them. We haven't technically even defined what an acid is. We've just been kind of like, hey, we're gonna name them right now, okay? Okay. And so that's a really excellent question. But for right now, you would actually find the things that you're talking about, you would actually find your polyatomic ions list. You're not wrong. They are actually acids, but we're not going to worry about those right yet. So excellent question. Hold it for another 2 chapters, and then we'll come back to it in chapter 9.
Okay, we have 2 more questions.
Sure.
So would hydrogen chloride be an incorrect answer if the state isn't specified?
So if we don't specify the state and you put hydrogen chloride, you would better be prepared to go to battle and explain why on an exam when we definitely covered binary acids and we barely covered what this thing is called, why this came to your mind first. So I'm going to go with yes, we would actually call that as being wrong, especially since I just have on here, assume it's an acid if you don't have any state. And I know in my class, I went ahead and said this, that if we forgot to specify the state, you should assume that it's an acid. But if that happens to you on the exam, you can always argue with us and see what happens. Arguing with the instructors doesn't always work, but if you're legitimately confused, you should always ask. But I'm going to go ahead and tell you that if we don't specify the state, you should assume that it's an acid. So you've got enough clues to figure that out. But I understand the wiggle room. I understand what you're asking, and I'm going to roll with, if you can identify it as an acid, you should name it as an acid. I also understand we should remember to put the AQ symbol by everything, but I'm just impressed the exams all roll out in 14 font and Arial, because that's a major improvement over last year. So, other questions?
Okay. The last question is, do we have to specify Roman numerals even for elements like FeCl with only one Roman numeral, so iron 1 chloride?
If you have something where it can have multiple charges, so basically here in this little block, I've got the group 1A, group 2A, aluminum, silver, cadmium, and zinc. If it's not in this set, you need to specify what it is. Because essentially, I understand that you're like, but it's just one of them. But if all I see is this, I don't know what that is. Like, and the assumption in nomenclature is that you're only communicating with one thing. So the assumption in nomenclature is that if we were to write it out all in words, I would just be staring at the words. And then I would be like, I don't know what this means, because I know a lot about iron in the body, and I know that in the human body, you got 2 charge states for iron. And one of these is useful for the human body and the other one is not. So if you want to say, oh, snap, man, I actually meant iron 1, that's not what I would be thinking about at all, because I'm thinking about hemoglobin. And so, but there's no way to communicate that without that. So you can't be like, well, if I don't specify it, I obviously meant this. With your transition metals, that's not going to work, because there's too many options. There's too many options. So you've got to specify what that is, if it has multiple options. Other things.
Okay, that's all the questions for right now.
Okay, cool. I have an outline. I'm gonna go back to my outline. Scroll, scroll, scroll. I don't remember what was supposed to come next. Formulas, math stuff. I got math stuff. Okay. So here's what I'm going to do on the math stuff is I'm also going to try to focus on things like wording. So for example, someone asked about various calculations and how these might work. So let's go ahead and ask something like, given 12.1 grams of, this is going to be cobalt 2 chloride. How many? And I'm going to use the word formula units. So you may or may not have heard of the term formula units. So realize that if I had a different question, and if I was asking about water, I would have likely used the word molecules, because water is a molecule. Water has those covalent interactions in between it, and water hangs out as molecules. They interact with each other, but you theoretically could go ahead and separate and just talk about a single water molecule. Completely possible. My cobalt 2 chloride, though, is an ionic compound. That's going to be that cobalt 2 plus and my chlorine -1. And so I cannot call that thing a molecule. It's not. So if I want to know basically how many sets of cobalt-2 chloride do I have, the best way to describe that is by a formula unit. Because really it's a repeating pattern. It's got that beautiful lattice structure, but I could describe it as a formula unit. So notice I've already scribbled all over this question, but basically be paying attention to different ways that this could be phrased. If I have an ionic compound, I can't describe that as a molecule. If I've got a covalent compound, I can describe that as a molecule. And the only point to all of this is to go from grams to moles, and back in chapter 2, this would have been from moles to atoms. So I'm still trying to make that jump that's going to use Avogadro's number. That's the goal. But I've got a couple of different ways to phrase that depending on if I have a covalent molecule or if I have an ionic compound. That's going to determine how this question is phrased. In order to do this, I do need my periodic table, which has run away from me again. So now what I'm looking for is I actually need the molar mass of cobalt-2 chloride. So here's my chloride ion. I have 2 chlorides. So 2 times 35.45. I only have 1 cobalt. Cobalt is over here, 58.93. This one I actually did not work out ahead of time. There's another one I did work out ahead of time because I knew I was going to need it. Plus 58.93. So I get in total, adding everything together, 129.83. This is grams per mole. So again, the old style, I would have gone grams to moles to atoms, but this is now molecules or formula units. Now that I have bigger things. So I'm still going to take my grams and divide that by my molar mass. Scroll down so I have some more space. So 12.1 grams of the whole thing. And there's 129.83 grams in 1 mole of the whole thing. And if I want to know about formula units, I'm going to say that in 1 mole of cobalt-2 chloride, I actually have 6.022 times 10 to the 23rd formula units. In my 8 o'clock class, I absolutely abbreviated this, and then I was a little bit sad that I abbreviated that. It looked like I just tried to insult the entire class. If you don't know what I'm talking about, try to abbreviate formula units and see what 2 letters you get. This is something that will be on your potentially useful information. That is Avogadro's number, 6.022 times 10 to the 23rd. So this is still a number that we do give you. It's on the potentially useful information page. So just because I have it memorized does not mean you have to. It will be given to you. It'll be at the very top of your periodic table. I'm going to divide by everything on the bottom, multiply by everything on the top. And I get something like 5.61. I'm going to do 3 significant figures because I'm going to assume that on the exam it has told me that that's what I need. 2 formula units. Now the other thing that could have happened is this also could have asked me for atoms. So it could have asked me for something like atoms of chlorine. If it did that, the thing I need to recognize is that in 1 formula unit, I actually have 2 chlorines. So I could have gone ahead and said for every 1 formula unit, I have 2 chlorines. And yes, I am just multiplying times 2. So there's 1.12 times 10 to the 23rd chlorines. So there's another variation I could have done. So instead of formula unit, I could have asked for atoms of something specific. That's an option I have. There's another option though. There is another option, and this is the reason why I picked the ionic one, because oftentimes you see the molecule option, or I think the molecule option sometimes is a little bit more intuitive because the molecules naturally stay together. But using the term formula unit sounds a little bit strange. So could have asked you for atoms. Also just could have asked you for total ions. So for doing total ions, then we're looking at the fact that I've got that cobalt 2+ and 2 fluorines. So that's 3 ions in a formula unit. If that's what I'm doing, then I need to take that formula unit number. Where did it go? 5.61. Formula unit. And say for every 1 formula unit, I actually have 3 ions. 1 cobalt, 2 chlorines. So again, I'm trying to think through different ways we could ask you questions that are relatively similar to each other, but then make what looks like a completely different question. So one set of math, backing this out a little bit. So we started off with, hey, here are some grams of a thing. Tell me how many somethings are in them. So realize that if it's ionic, we could ask you about the formula units, which is an analog to molecules, or we could ask you about a number of atoms, or we could actually ask you to break that ionic compound down and tell me about how many ions are in there in total. Overall, you're still going to go from grams to moles, and then moles to formula units. And then the question is do you need to go any farther than that? Also, if you've done this kind of problem before, I've gone ahead and done everything where I go ahead and basically do the old math we used to do in that same order, where I've gone ahead and gone from grams to moles, and then from moles to using Avogadro's number to get to a really big number. If you've done this kind of math before, you may have already seen this and you may have a different strategy because there is a different order to put the calculations in. You get to the same answer though. So here's what I'm talking about since I've danced around it without actually saying it. So if I was trying to do total ions, you could have actually started off with that 12.1 grams of the whole thing, and then gone from grams to moles, scrolling back to grab my number, 129.83 grams in 1 mole of the whole thing, cobalt 2 chloride. This is the point where some people would actually say, now wait a minute, for every 1 mole I have of cobalt 2 chloride, I actually have 3 ions. And then I could say that 3 moles of ions, by the way. 3 moles of ions, and then I could go ahead and say for every 1 mole of ions, I actually have 6.022 times 10 to the 23rd ions. So some folks may remember from high school doing this in a different order. They both work. they will get you to the same answer. That is one of the beautiful things about multiplication, is it doesn't actually matter what order you do it in, you get to the same answer. As long as you're still multiplying by the things you need to multiply by and divide by the things you need to divide by, you get to the same place. So it doesn't matter when you take that factor of 3 into account, as long as you found the right factor, you'll be good to go. It's 5:30. Questions so far?
No new questions.
Like we didn't, I know I did a lot with language, but hopefully this was mostly a review of the math and then adding on some different words we can use. So equations using a combination of these concepts, that was also what I was trying to do, is try to point out that we can go from grams to moles, moles to formula units, all of that jazz. I did go ahead and make an example calculation that does the percent composition to empirical formula, just because usually people are looking for more of those. So one of the other questions that we sometimes have is something that says something like this. A sample contains 27.35% sulfur, 31.75% iron, and the rest is oxygen. What is the empirical formula? So notice so there's this kind of question. The other kind of question is just the one that will say something like, what is the percent composition of oxygen in water? I know it's a really straightforward one. And so for this kind of question, we could say percent composition. We could also say percent by mass. We could also say the mass percent. I think those are the only options. So again, trying to think through different ways questions can be asked, different ways questions can be formed. The way percent composition does work is essentially all we really need to do is take water, and I should have 2 times that 1.008, 1 times 16, to give me a grand total of 18.016 for my total mass. And then I just need the contribution of my, that's for oxygen. Actually, I want to do hydrogen. I changed my mind. Sorry. So the percent composition of hydrogen in water. So I'm just going to take the contribution of all of the hydrogens. So that's 2.016 divided by 18.016. And whatever times 100%. Don't forget that. It's tempting. Don't forget that. So 18.06 times 100, 11.2%. Okay, for this other question, so that's percent composition. The nice straightforward way. For this one, there's only really 2 ways this is typically phrased. One way has percentages, the other way has grams. So granted for this one, if it was grams, and again, I'm this is going to seem a little bit silly, but this is what I'm going to do. I could just say a 100-gram sample contains, and then it would say something like 31.75 grams iron and 27.35 grams sulfur, and the rest is oxygen. What's the empirical formula? You can't really avoid the words empirical formula. So when you're looking at this kind of math question, we pretty much have to say empirical formula, because that's really the only way to ask how to go from either grams or percentages and wind up with a formula. Because without additional information, you can't really get to a molecular formula. So this usually has to ask for that. If it's really straightforward, you could potentially say, what is it called? The one I have is not straightforward enough to name it. But if there were only 2 elements and it was an ionic compound, it's possible to actually ask you for the name. So instead of empirical formula, they could feasibly ask you to name the compound. But again, the one I have set up will not work for that. Will not work for that. It is too complicated. It works fine for empirical formula, but it would not work well for naming. Let's go ahead and do this one. So the reason why I have percentages and then I said 100-gram sample is because if you do have percentages, the easiest thing to do is to assume you have 100 grams. So this is a trick that I use all the time, which is if given percentages, then just assume you have 100 grams. Makes your life way easier in what you're doing. So if you have percentages, just go ahead and assume that you have 100 grams. Life becomes much more straightforward and simpler. So hopefully I'll have watched Dr. Diekman's video on this, because this really is one of those where you just have to follow. It's not really a formula so much as it's a series of steps. So what we have is we have iron, sulfur, and oxygen, and I'm told that we have 31.75 grams of one of these, 27.35 grams of another, and the rest is oxygen. So I'm going to do my subtraction. 100 minus 31.75 minus 27.35, and I'm going to get something out of this, which is 40.9. The goal is a formula. The goal in a formula is to be in multimole ratios. I have grams and I want moles. We have been here before. So since that's what I want, all I'm going to need is my periodic table, because then what I'm going to do is I'm going to grab the atomic masses of each one of these and divide each individual mass by its atomic mass. So I'm going to take my iron and divide it by 55.85, my sulfur and divide it by 32.07, my oxygen and divide it by 16. When I do that, I'm going to have moles. I'm going to have moles of all of them, which is what I wanted. So I can start to think about an empirical formula already. So my iron is 0.5685, sulfur 0.8528, and my oxygen. So these are all mole to mole ratios, 2.55625. Yay, I have mole to mole ratios. This is not an empirical formula though, because they're not whole numbers. I need whole numbers. We're going to use a math trick and divide everything by the smallest number. essentially, now that I have mole ratios, I want to keep those mole ratios. So I'm going to pretend that this is an algebraic formula, and whatever I do, I now have to do to everything. So whatever I do, I have to do to all of them. I got a 1, that's a whole number. I like that. I got 1.499. I don't like that. I got 4.496. And I wrote the number 5. 496. I don't like that either. So hopefully when you see this, you can think, okay, well, this is really about 1.5. Since I see that 0.5, I'm going to multiply by 2. But remember, I got to keep it all together. I finally have everything in the ratios I want, so I have to keep this all together. So this is Fe2, S3O9. And that's my empirical formula. I think I already mentioned this one is too complicated. We would not expect y'all to name this because it's kind of a mess. So no naming on this one. If all I had was iron and sulfur, you could handle that. But I wanted to make sure I got to do that multiply times 2 thing at the end. So I wound up with something a little bit more complicated. So I have done an example of the math. We've mentioned before that naming sometimes gets a little bit wonky, that there can be a variety of different names involved, but overall, we've at least gone through one example of the different sorts of math involved. I did skip over very quickly how to put together those molar masses. So we can just ask you for the molar mass of a compound. That also has a couple different names: molar mass, formula mass, molar mass, formula mass, molecular mass. But you'll notice there is that commonality in between all of them. So I will also comment molar mass, formula mass, molecular mass. And hopefully we don't do this because we should be better in our vernacular, but we could say molar weight. We could say formula weight. Basically, I say we should be better than this. If I write the problem, there's a good chance that I'm going to slip and say molecular weight, because molecular weight's a very biochem thing. I've tried really hard to get rid of that, but sometimes it slips out. So molar mass, these are all the same thing. I understand that weight technically means that gravity matters. I also understand that formula mass should only be for ionic compounds. Molecular mass should only be for molecules, and molar mass works for both of them, but they're all asking you to do roughly the same thing. Okay. Questions so far? Any of the math stuff?
No questions about the math, but there was a question. Will we have to know how to name organic compounds containing functional groups other than alcohol?
No. No, you don't. Nope.
Okay, that was all. Oh, there's one more question.
Sure.
So to find the empirical formula, we never round up, just multiply them all by the same number that turns them all into a whole number?
Yes. I'm saying it like that because what you should be on the lookout for is, you may have noticed I had things like 1.499. So I did a little bit of rounding, but you should be watching out for, if you have something that's basically like 1.5, you're going to multiply that. 1.33, you're going to multiply. 1.75, you're going to multiply. About the only time you get to round is if you have 9. When it's a 9 or like a 0.01, then rounding is okay. But for the most part, you're going to avoid rounding. But technically I did round. It was really small rounding. And I know that seems a little bit vague. Practice helps with this. So do check out those again. In the chapter problems, Dr. Diekman's video has an example. I know in my class I pulled out a different example because these are ones where you get kind of a little bit used to the fact that the numbers are very rarely perfect. So usually small roundings happens, but being on the lookout for things where you need to multiply out and making sure you multiply everything when you do that.
Okay, that's all the questions we have right now.
Beautiful. So one of the questions that I got beforehand asked about deviations from ideal bond angles and how that's different, how it's handled on an exam versus a lab. So from what I am told, in the lab, you had to give exact numbers. Here's what this usually looks like for us. So what usually looks like for us is we would give you a compound, and then we would say has bond angles of. And it might actually even be nice, and it might say actual bond angles. Maybe it says real bond angles, but it somehow is meaning that it's not the ideal. You would need to be able to draw this. So this is ammonia. So this is one where I'm going to do this really quickly without the periodic table. You would get your valence electrons from the periodic table. Let's say nitrogen has 5 plus 3 times 1. That's 8. My nitrogen goes in the middle. No atom left behind. So all my hydrogens go around it. So that's 6. I have 2 left over. There's a lone pair. So as I'm trying to draw this now, I got my lone pair on top. I got a hydrogen. I got a hydrogen coming out at me. This is a dash, by the way, trying to show it's going out of the page. And I have a hydrogen going behind. I could identify this with an electronic geometry of tetrahedral, where I count 3 bonds and a lone pair. I could also identify this of a molecular geometry of trigonal pyramid, or sometimes it says trigonal pyramidal. So those two things should be different because of the lone pair. This lone pair is going to basically squish the bonds. If I had ideal bond angles, my ideal bond angles would be 109.5 because that goes with the tetrahedral. The question, ask for the actual or the real ones. There's a couple different ways to do this. Either we could say for my actual bond angles, we could either just say less than 109.5, greater than 109.5, 109.5, exactly. And then we would do the same thing with things like the bond angles for trigonal planar, essentially trying to throw you off, thinking that maybe you forgot that there's a lone pair on there. So this is one potential set of options. And what we're looking for again is that bond angle is going to be squished. So we would be expecting the answer to be less than 109.5. So this is one option of what test deviations would look like. This is one option. Here's my other option. And it's based on the exact same principle. My other option would look like this. 107, 111, 109.5, 119, 122, 120. And here again, what I would do is I'm still looking for the thing that's less than 109.5, which is this one. So on an exam, we would not expect you to know exactly what that bond angle was, but we would expect you to know that it's less than 109.5 and that you could pick less than 109.5 out of a lineup. So we could give you real numbers. We could. But if we do that, there's only going to be one answer that's less than 109.5, but bigger than 90. So some other wrong answers that could be on here is we also could have done things like 89, 90, and 92. So realizing that when we're looking for less than 109.5, we're looking for something that's still close to 109.5 as we pick things like this. So we could just do less than 109.5 and do it in symbols. That is one option. We have certainly done that before, but we could also give you numerical options. But I think on your lab, I think they were expecting you to use some other like cloud-based software so that y'all actually could figure out what the real bond angle was, and then they made you like input it and actually like give a value, which is really cool. But e-learning is not that fancy. So we're working with e-learning where all we're going to expect you to do is basically analyze with a pen and paper. And from a pen and paper, all you can really say is, hey, that should be less than 109.5. Okay, so great. There's now like 9 different numbers. And out of these 9 different numbers, 3 of them are focused around a bond angle of 90. 3 of them are focused on a bond angle of 120. 3 of them are focused on a bond angle of 109.5. It's a tetrahedral electronic geometry. I'm looking for a bond angle around 109.5. That one lone pair makes the bond angle deviate and squishes it down. So I'm actually looking for that bond angle of 107 or less than 109.5. So in this case, I'm looking for that 107 because that's the best answer out of the set. So that was a question that came from the questions asked before the session started. And I wanted to make sure that I covered that because it's a good question, especially because your lab is training you guys, and your lab this past week has been really helpful for the exam coming up. So I just want to point out how those things are similar because the lab is actually really helpful to the exam, which is really sweet, which is really awesome. I like it. So I want to make sure you guys are getting the most out of your time spent on that lab. Questions so far?
There are not any more questions at this point.
Okay, cool. So I know we're coming close to time. So what do I have left? Do that Dr. Diekman thing and make a second video. Always fun. Okay, so we did all of that. We did that. Oh, I cannot do polarity in 7 minutes. Actually, there is one thing I can do that will be helpful and goes with the theory the concept we've been doing about language. Let me talk about the language for a moment. So in chapter 6, so I'm going to talk about polarity. That is what I'm going to do until I run out of time. That's what we're going to do. Okay, so in chapter 6, y'all actually were introduced to the concept of polarity, and we did polarity with bonds. And when we did polarity with bonds, what we used, and what we're going to use again, is electronegativity. So essentially, the bigger the difference, in electronegativity, the more polar the bond. So we had things where we could find our periodic table, and we could have things like a carbon versus a fluorine, and that bond we would expect to be polar because the fluorine is a very electronegative atom, carbon, not so much. We could have things like a carbon-carbon bond where we would expect it to be basically non-polar because it's the exact same atom that is trying to pull through that bond. As we move forward into polarity and when we're trying to look at molecules overall, there are really 2 times you are going to be like, not polar, no way, no how, not polar. As far as bonds, because this is all bonds so far. So we're talking about a nonpolar bond. The main times you're going to worry about this, one is when it's a carbon-hydrogen bond. Now, I understand that you can go to your textbook, you can go back to chapter 6, and you can look up the electronegativity values for carbon and the electronegativity values on the Pauling scale for hydrogen, and you can tell me that they are not identical. I know you can do that. I am telling you, as both someone who writes your exams, and I'm also telling you as a person who lives in the world, polarity of molecules usually revolves around water. And I don't know if you've ever tried to get butter, grease, oil of any sort off of your hands with just water. It doesn't work. Butter, oil, grease are made up of basically nothing but carbons and hydrogens, and they don't mix with water. And that idea that they do not mix well with water is going to have us define them as being nonpolar, because that is the way that the world we live in works. So I understand that you can go to your book and argue with me, but then I'm going to try to get some like vegetable oil and put it on your hand and ask you how long it takes to get you to get it off with just water. And the other time we have a nonpolar bond is when it's the same element. All the other times, you're going to assume that there's some sort of polarity going on. Maybe not a lot, but a little bit. But nonpolar bonds, carbons and hydrogens, or when it's the same element. Now, I've only used 2 words. I've only used polar and I've only used electronegativity. Let's go ahead and talk about some other words, shall we? Let's use water for this. So, this has dipole moments. So this has polar bonds, so oxygen to hydrogen, polar bonds. When I'm noting a polar bond, I could draw a dipole. The dipole is the arrow thingy. It points to the negative part. And a dipole is also trying to show that there's an uneven distribution of electrons. Even distribution of, I'm going to say negative charge. If I draw the dipole moment of the entire molecule, I would just point to the oxygen. So this one is for the molecule. The little ones were for bonds. What is going on with my writing ability? It's going downhill. So there's polar bonds. There's also a dipole. I could also draw on this thing a partial negative charge and partial positive charges. So this weird little symbol I drew, partial, and essentially it's to try to separate out the differences between something that's polar, where it's got a little bit of a charge. There's more negative stuff where the oxygen is. There's less negative stuff where the hydrogens are. It's polar, but this partial helps me differentiate that from whole charges. So when we were looking at ammonium chloride, or we were looking at cobalt 2 chloride, or any of those, and I drew giant charges, +2, 9, -1. Anytime I was doing those are whole charges. These are just partial charges. So it's another way that I can talk about what's going on in a molecule that is not using the word polar. So polar bonds, dipole moment, partial charges. I'm trying to think if there's another one. So what I would recommend you do is go back through your notes and see if there is another way to talk about or to denote what's going on in here. Because polarity and electronegativity, maybe that's the other word I was looking for. We'll say differences in electronegativity. There's a lot of different words and they're all being used for the exact same concept. So this is both a time where if there was some sort of true-false setup for this, it's really easy to get caught in the language. Or it's also a good time to make certain that you're comfortable with the different ways that we might try to indicate to you that we're trying to give you information and help you. One of the things that sometimes happens on these exams is sometimes we'll go ahead and be like, well, geez, we can't have them draw every single Lewis structure. That would take too long. Let's draw some of them for them and let's help them. So if you don't recognize that a dipole is trying to tell you, hey, by the way, this is a polar bond or a polar molecule, or hey, this is a symbol for a partial negative and a partial positive charge, this is actually trying to help you, then those symbols that we're usually trying to use to give you information, you need to be able to translate those so that they're in something that you understand. I did not actually succeed in talking about how you figure out if a molecule is polar, so I am missing information. Nor did someone had asked what an isomer was, and that information is not here either. So what I'm going to wind up doing is eating dinner, and then what I'll probably actually do is I made the videos for the pre-recorded lecture videos. So what polarity is, I've technically already made a video on that. I understand that sometimes people want it again. The hard thing is that honestly, if I did polarity again, it's going to sound a heck of a lot like the pre-recorded video that I made for chapter 7. So that was already going to be there. So what I will probably do is either in some notes form, possibly in a video. I may answer a few more of these because we'll go ahead and do something that talks about what an isomer is, because it's not something that you're really responsible for, but we may use that term. So I'll point out what that term is. And then are there any questions out of the chat that I can answer right now before we go, since it's a little bit after 6?
No, there's not, Dr. Taylor, but thank you so much.
Yeah, no problem, no problem. So yeah, it is 6 o'clock, and I will put something together. Honestly, for polarity, it's just going to be a link to the Microsoft Streams video from chapter 7, because otherwise, if I made something new, it would be exactly the same. But I can go ahead and answer the isomer question, and I can go ahead and answer the PX, PY, PZ thing that I did not get to that I alluded to at the beginning of the thing. So I will put that together later this evening, but first I'm going to go eat dinner. So I'm going to sign off for now. Have a wonderful day. Have a wonderful evening. Your exam is October 23rd, and you need to log on as close to 10 a.m. as possible, because we will shut that thing down at 10:30. So make sure that you are logged in at 10 a.m. 10 a.m.
Thank you, Dr. Taylor. Have a good night.
You too. You too.